All right, recording is rolling. Welcome to Thursday, September 14th. So yesterday at the tail end of class, we were looking at Newton's laws of motion. I'm going to break this out for a quick review, and also we're going to look at Newton's second law of motion here, how those units line up. We got a mystery cut puzzle for you guys. Most of class, we're going to be doing some free body diagrams. Oh, I see notebooks out. You guys got notes out. Awesome. Do a bunch of those. What's due tomorrow? Projectile motion quiz. There you go. Right. And at this point, I'll probably use this video for all my classes because I'm doing similar type thing. So at this point, the quizzes are all handed back, so you guys can do corrections for partial credit back there. All right, let's look at Newton's laws of motion. You guys saw the tail end of yesterday. Hopefully, you guys know these by heart, or if not, then you will pretty soon. Make an effort to know these. Newton's first law of motion: object at rest will remain at rest. Object in motion will keep on doing what it's doing. Nothing's ever going to ever speed up, slow down, or change direction unless there's an external force acting on that. That's also called law of inertia. It's synonymous with first law of motion. Second law of motion: where do accelerations come from? Because you guys know what acceleration is. It's something to do with like a rate change in velocity, right? Which might be speeding up or slowing down. And a few weeks from now, we'll get to like turning, like changing direction. But what is the magnitude of that acceleration? What is it, right? So it's directly proportional to the net force acting on it, but also inversely proportional to its own mass. Now, when I say net force, there might be multiple forces acting on an object, but you have to say, maybe add these together with components, or maybe do like Pythagorean theorem if they're the right angles, right? All right. You have to figure out as if there was a single force, right? If there's two kids kicking a soccer ball, one straight north, one straight east. Okay, it's as if there's a single force going northeast, right? With some magnitude in some direction. Vector quantities, right? The more force, the more acceleration. That's a direct relationship. The more mass of the object, the less it will accelerate for the same force. Ooh, that's an inverse relationship. You guys get that? Okay. Now, I really prefer the fraction form myself. I think it shows cause effect better. A lot of textbooks just write it in the non-fraction form, F equals ma. If you ever ask, what is Newton's second law of motion? You say F equals ma, boom, you got it. Of course, the net force, right? And here's where I want to pause and go look back at this the starting card right here. Right? Oh, there's Newton's second law of motion, right? The net force is mass times acceleration. Okay? Now, you guys remind me, what is the base unit of mass in the metric system? Not grams, but kilograms, right? Which is like 1,000 grams, right? Kilogram, right? Now, why is that? Here's where this starts to actually become important. What is the unit for acceleration in this class? Meters per second squared, right? So it's somebody's changing velocity, meters per second per passing second, and so we'll call it meters per second squared. Right? Now, if you multiply together the unit, notice this is variables up here, this is units down here. If you multiply together kilograms and meters per second squared, that is the definition of 1 Newton. 1 Newton of, and what is Newton's measure? A force, right? Weight is one type of force, right? So it could be force, weight, that kind of thing. Right? I have here a 100-gram lab mass. How many kilograms is that? 0.1 kilograms, right? And how much does this weigh? If it's how many newtons of downforce is this? 1. This is 1 Newton, right? Actually, like 0.98 newtons. I'll just call it 1 Newton, right? If I drop this, how much is it accelerating? 10 meters per second squared, about 10 meters, right? 9.8, 10 meters per second squared, right? Oh, look at this together. So I got 0.1 kilograms. It accelerates 10 meters per second squared because it's under 1 Newton of force. 0.1 kilograms times 10 meters per second squared is like 1 Newton. Right? Or let's go back to the fraction form, which I really prefer, right? Think in terms of this, right? If I have 1 Newton of gravity force, right? Gravitational force, 1 Newton of weight, acting on 0.1 kilograms of mass, it's not going to result in 10 meters per second squared. Right, you guys see it? There you go. It's second law of motion right there. Let's see if you guys are really following. Question for you guys. If there is a constant net force on an object, constant net force, does that result in a constant velocity or a constant acceleration? Which one?
Constant acceleration.
Boom, constant acceleration. There you go. Newton's second law. All right, well, we got Newton's laws out. Let's hit the third law real fast again. This is the equal and opposite rule. For every force, there's an equal and opposite reactive force. You need two objects that are pushing or pulling on each other. Okay? So whenever some pushing or pulling, think about two things interacting. Right? Example: cannonball and a cannon. How? There's a force. There's force on a cannonball during that explosion. Yeah, that's what gets it in motion. Is there also like a recoil type force on the cannon? Yeah, because it sends the cannon back the other way. Right? But which force is bigger? What? Equal. Can't get you guys. Equal. Same force, right? hang on, how is it the same force? Because I see a huge change in motion in the cannonball. I see a small change in motion in the cannon. Why? Because those two objects have different masses. That kicks back to the second law. Same force, different masses, different changes in motion. Ah, right, right. How about the Earth and the Moon? Does the Earth pull on the Moon? Yeah, it keeps it in orbit. Does the Moon pull on the Earth? Yeah, we get tides and stuff, right? But which force is bigger? The same force, right? Different masses result in different types of motion. Right, here's a different perspective on Newton's third law. Now, suppose there's some kind of gravitational attraction. Right, we'll talk about a few weeks from now. Right? Now, if they were 1 kilogram floating out in space, obviously that would be equal opposite force, right? Same mass, same force, right? Right. And that kilogram, and that kilogram, and that kilogram, and that kilogram, those could all be definitely like intuitively equal. Okay. Right. Now let's see the aggregate effect. What if it's like 3 kilograms versus 1 kilogram? You guys see it's still the same gravity force of attraction? That could be like the Earth and the Moon type thing. Right. Right. So main thing today, we're going to look at a bunch of free body diagrams. I'm going to give you guys some scenarios, see if you guys can draw what the free body diagrams are going to look like before we get there. But I want to hit a pause before I hit this because I've got a classic physics puzzle for you guys. Classic puzzle. I get my paper protection here. Classic physics puzzle. All right. So I got this cup here. Oh, look at this cup. Oh, this looks like a normal cup. No, nothing weird looking about that cup. Okay, it's something glued together. Something funny looking. Okay. Oh, what's that? Is that a hole in the bottom of the cup? I would have a hole in the bottom of the cup. Let's flip this over. Yeah, it's definitely some kind of straw hole going on there. What's the deal with that straw? I wonder if this works as a normal cup. Let's find out. So I'm going to fill this halfway up with water right here. All right, let's take a look. Yep, it's filled halfway with water. You guys see it's filled halfway with water? It is holding the water. Okay, so maybe it does work as a cup, right? Right. Now what I do, let me take it over here to the sink. I fill it all the way to the brim. This cup goes back a couple thousand years to ancient Greece. Oh, look, now it's leaking out the bottom. Let me bring the video camera over here, the camera, so we take a look at that. Now it's leaking out the bottom. So back in the day in ancient Greece, they would give guests this type cup, say fill it like halfway, and then the guest is greedy. I want more, give me more water. I don't want to make an evil, maybe he's a poor thirsty guy, right? And then fill it to the brim, and then there's water, everything's all wet, and then the host like until right, whole cup. Shake out the last dregs right there. Whole cup drains. Let's bring this back over here. Look, where'd all the water go? It's all gone. I got an empty cup. So let's do a recap. Let's do a schematic here. What you guys just saw. What you guys just saw was do a cross section right here. Cross section type. So here's cross section. Okay. We looked at the top of the cup, down at the bottom, saw like something like a straw there. Flipped it over. So, okay, see like a straw leading at the bottom there. So something to do with that, right? Like, how's this thing working? What's the deal with this guy? So I filled it halfway with water, right? And the water stayed in the cup. So it's all fine and good. So that's all fine and good, right? Then I filled it to the brim, and water starts pouring out the bottom. Right? But now here's the weird final catch: is that the water level doesn't just go back to the previous level where it was perfectly fine before. No, like the entire cup drains. Ooh, right? So challenge question for you guys is, what's going on inside that cup? Here's what we're gonna do. I'm gonna let you guys think about that for a day. There might be a couple of you guys out there that might know the answer or be onto something, but I'm gonna give everybody equal opportunity, a day to think about that. We'll come back and we'll revisit this tomorrow. Right? You guys get that? All right. So got a cup puzzle. Yeah. All right. So free body diagrams. I'm about to pull up a PowerPoint while I got this slide out. Let's take a look at this. Free body diagram. We're just gonna we're looking at a diagram that just shows all the forces acting on an object. Okay? Now, closer to December time, we'll talk about like torques or moments to get some kind of turning type motion. But for the next few months, all I care about are forces. Now, you guys know that there are different types of vectors. Lots of vectors we looked at in this class. We look at displacement vectors, velocity vectors, acceleration vectors. Right? With these diagrams, all I care about are force vectors. Right? Right? Because like velocity vectors, for example, like here's the tricky thing with velocity. But are you in motion right now, or are you at rest? Well, kind of depends on what you're trying, like relative to what, right? Maybe you're at rest, or maybe you're like, wait a minute, I actually am on a giant spinning planet. But you can't really feel the difference, right? But you could feel the difference if there's some kind of force which might result in some kind of acceleration, right? So here's like object in free fall. If you ever see free fall, you're just thinking, well, there's only one force, its own weight, so it's accelerating straight down, right? Toss us off the edge of cliff, W, right? A couple days back, one of the tasks I had you guys do was take a spring scale, hook it to a lab mass, and like drag it constant velocity across the surface, constant velocity. Okay? Now, guys, when I say constant velocity, what's the acceleration? 0. Therefore, what's the net force equal to? Also 0, right? If there's no acceleration, there's no net force, right? That doesn't mean that there's no forces. It just means that the forces are all zeroing out. Right? They're all canceling each other out. Right? Let's take a look at this one right. See, like if you're pulling constant velocity across the surface, that is an example of equilibrium because all the forces are canceling out, right? So let's look at these forces here. Right, so we got the weight. I was going to ask you guys with the free fall. I meant to ask you guys, M times G. That's how I'm representing weight in this class. Is that two variables multiplied together? Mass times gravity field. Is that what that is? Right. Versus, let's say you go home and you have a bottle of Advil or something, right? If you saw mg in that context, that would represent what? Milligrams as a unit, right? But in this class, you see m times g is two variables multiplied together. That represents the weight. Right? Sometimes for AP, you'll see F sub g, like gravitational force. Every once in a while, I might use that too, but I tend to use m times g. All right. Now, if there was just if the weight was the only vertical force, then it would be back in free fall, right? But do you guys think there's some kind of support force from the surface holding it up? That's what this guy is here. This is support force from the table, right? Did I tell you guys yesterday? I forget if I did. What the N stands for? What kind of force is that called? Normal. And do you guys remember from a math class? If two lines are normal, that means they're what? Perpendicular. Normal is a synonym for perpendicular. This normal force is always perpendicular to the surface, right? If the surface is horizontal, the normal force would be vertical, right? Right? That's what normal means. So it's like the perpendicular force, right? Okay, so these two are balancing out so that there's no acceleration vertically. In fact, there's no motion vertically, right? But so you're applying a horizontal force, like an applied force. You can call this spring force, applied force, pulling to the right. You guys are reading straight off that. But if it was going constant velocity, yeah, that's zero acceleration. That's zero net force. There must have been some kind of resistive force there too. Like the friction force, right? In fact, those two would exactly equal in magnitude if it's constant velocity. Isn't that true? Like I said, great. So we'll see that in PowerPoint. I got a few more things to say about that, but I'll say that when we get to the PowerPoint slide. Right? Here's a little trickier one, the one in the middle. I like it like an incline. Right? There's a whole class of classic physics problems that involve blocks on inclines, and we can get kind of crazy and fun with those. But just a very fundamental example, it's a block on an incline. Right? So yeah, its weight is the same as it would be, however else, right? Earth's gravity force pulling down, right? Look at this normal force. Is that perpendicular to the surface? I think it is. I think it has to be. That's why it's the normal force, right? I bet that normal force is slightly smaller in magnitude than the weight. Right? Maybe the weight's like 10 newtons. Maybe this is like 8 or 9 newtons. Right? And then there might possibly be a friction force, possibly too. Right? That might be trying to oppose the motion. Right? You guys good with that? Let's flip over to a PowerPoint. Oops. Let's get this thing going. All right, move this here. Come on, bump this, bump that. Zoom. All right, where's my? Okay, hold on. Let me try this again. Share screen. Great. Okay, we're up here. All right, free body diagrams. Okay, so you guys got your notes out. A diagram showing all the forces acting on an object, and then in December maybe we'll add torques to that. Okay. So you want to draw force vectors to represent the relative magnitude and direction of each of the forces. Okay. So whichever direction the arrow is pointing, that's also the direction of the force. Right. Talking about vector quantities. Right. But also the magnitude of this thing. So if I have two force vectors, you see how those two force vectors are the same magnitude, right? The arrows are the same length. That means the force is the same number of newtons. Right. For AP, advanced placement, always draw, there's a convention here, always connect the tail of each vector to the center of mass dot. You see the center of mass dot as if that object is a single point, like point mass, and draw the force vectors extending away from that center of mass dot. You see that? Right. Now, word of caution here, the solutions that you guys have for your chapter 4 puzzles, I did make those a few years ago before I knew this convention from AP. So I didn't always follow that rule. There might be like force vectors that aren't connected to the center of mass dot, but since I realized this was a rule, I've made all all my posters are following this rule, right? The force vectors are connected to the center of mass dot. AP is really strict about this rule. I've seen AP graders talk about like, oh, like a student had an FRQ and they drew everything right and we clearly knew what they were talking about, but their force vector missed the center of mass dot by like 1 millimeter, and they sat around the table like, no points for you. Right? So you guys know you're going to connect your force vectors to the center of mass dot. Okay, right. Forces are measured in what? Newtons. Right now that's metric system, which we're using. Right? Do you guys know what the American unit is for force? What do you measure your weight in? Pounds. Right now, here's why where pounds gets really messy. In US units, which came from England, pounds is used for both mass and force. They call it like pounds mass and pounds force, right? Which gets really icky, I think, because those are totally different concepts, right? I mean, one's a scalar and one's a vector. No, that's totally different things, right? But the metric system is really good at distinguishing between those two. Masses in kilograms, forces in newtons. Okay? Velocity vectors are not force vectors. Acceleration vectors are not force vectors. So those are not going to show up in your free body diagrams, right? Just forces. All right, here we go. Block at rest on a table. Can you guys draw that? So, right, premise in your notes. Block at rest on a table. Draw a block. Draw a dot. Try to flip through this at a pretty good pace here. Right. Some of these should be pretty straightforward. Maybe seeing some of these. I stretch your imagination a little bit, but maybe that's good too. Right. Oh. All right, so maybe there's like one kind of most obvious solution to this, although some of these might have multiple solutions, right? But this block has a weight, right? So it pulls straight down. I mean, if it didn't have that, it's just like floating out in space, then it's kind of hard to satisfy that condition, right? So the weight's pulling down, and there's a normal force supporting it that way, straight up. Right, guys got that? Right, boom. That could be it. That could satisfy that, right? Anything you see just at rest on any of these tables, yeah, that's the free body diagram on every single one of these objects just sitting at rest. Weight down, normal force up, right? Guys, if you ever see F sub n, I am talking about the normal force, not the net force, right? I might either write out the subscript, the word net, or do like the sum of forces for the net force. Right? What is the net force on that block right there? Zero newtons, because these two cancel out. There's zero net force. Right. What about, next slide, there's a block on a table, pushed horizontally, but with not enough force to overcome the friction between the block and the table's surface. Right? I might specify and call that static friction even, right? Right. So say we're pushing on the block, but it's still at rest. Right. So there's still a weight pulling down, right? M times G. There's still a normal force from the table supporting it. I guess we got a horizontal table. Right? Good assumption. Right. I'm pushing on it with a certain force. I might call that F push, F applied. There's some kind of push going on. Right. Now, if I stopped right there, would that could that represent the block at rest? No, because there's a net force on it. Right. So I need what else? Bam, a friction force that opposes the applied force. You guys see that? Right. There you go. That's the block at rest. In fact, that could also have been an example of the previous slide. I just said a block at rest on a table. I mean, that's also a block at rest on a table, so that would work too, right? Is that okay? All right, I have a follow-up question for this one while you guys are finishing that. Right. Tricky question here. You guys remember Newton's third law of motion? For every force, there's an equal and opposite reactive force. Right. What is Newton's third law reactive force to the weight? Like here's the Earth pulling down on the block, right? Is that mg, the Earth pulling down on the block with the gravity force? What is the third law of force to that force? And it's not the normal force. It's not the normal force, right? Although those are equal and opposite, but not because of Newton's third law, right? Do you guys know what is the opposite force to the Earth pulling down on the block? The Earth pulls down on the block. What do you think? How about, no, that's a normal force, not quite. Right? The Earth pulls down on the block. Does the block pull up on the entire Earth? Yeah, that's that one there, right? Whenever you think about Newton's third law, force pairs, consider that there's more than one object, right? So we got the block and the Earth here. There's a block-Earth interaction. That block is pulling up on the entire Earth, right? So the Earth pulls down the block pulls up on the Earth, right? But which of those forces is the larger force? The same force, right? Hey, what's the Newton's third law of force to the table pushing up on the block? That's the one listed here. The table pushes up on the block. The block pushes down on the table, right? Right? Could it ever be that the weight and the normal force are actually different magnitudes? Could that possibly be? Hey, what about this? What about, think back to your lab a couple days ago. You guys remember one that was called elevator weight? What if you walk into an elevator and the elevator starts accelerating upward? Ooh, Earth's gravity pull doesn't change. But if you're standing on a scale, I bet that scale rating is changing. I bet there's a larger normal force than there is a weight. Ooh, right? Does that make sense? Right. Or vice versa. If the elevator accelerates down, I bet that normal force decreases. How about you push on the block to the right? Does the block push back on you to the left? That would be Newton's third law to this one, right? And there's some kind of frictional force from the surface acting on the block here. What's the Newton's third law to that one? The block pushing back against the surface to the right, right? If this whole block was on like a piece of paper, do you think the paper's trying to slide to the right because I'm pushing to the right? That would be the equal and opposite to this friction force right here. It goes both ways. Okay. All right, next one. Block on a table, push horizontally so that the block moves at constant velocity. Oh, we just did this one both yesterday and today, right? So we got the weight, the normal force, the applied force, and the friction force. Okay, so now it's just sliding, right? Oh, but hang on a minute. That one looks identical to the previous slide. In the previous slide, it was at rest. And this one, it's sliding. Right? Guys, if you only had that free body diagram and you had no other context, would you know if that block was at rest or moving at constant velocity? Would you know? No, because those two free body diagrams are identical. Right? The only way you might be able to know is if I specified if it was static or kinetic friction. Static friction is the previous slide. This friction this slide could be kinetic friction, right? Where the surfaces are sliding past each other, right? But if you didn't know that, it would be ambiguous. You wouldn't actually know, right? One more thing, since you guys do know that it is in motion, I did put a velocity arrow out here to indicate direction of motion. The only thing that's good for is the friction force does oppose the direction of motion. So that is like a universal rule. So if you know the direction of motion, as a rule, you can always draw the friction force opposite of that. Block on a table pushed horizontally so that there is a net force. Ooh. Okay. So maybe the most obvious thing to do is, okay, we got a weight, we got a normal force, right, holding it up, right? And maybe you're pushing more than the friction's acting. Okay. Now that block, is that block in equilibrium? Definitely not. There's definitely a net force. There's a net horizontal force, right? So is that block accelerating? Yep. Right, so subtract these two horizontals, you get a net force, divide by the mass of the block, tells you exactly how much it's accelerating. Okay. Furthermore, while you guys are finishing notes on that one, furthermore, I know that block is specifically speeding up. Here's how I know it's speeding up. Guys, which direction is the net force? To the right? So that means the acceleration is also to the right, right? Okay, so I know it's accelerating to the right because of how the forces are, right? But I furthermore know that the velocity is also to the right. How do I specifically know the velocity is to the right? Because the friction's to the left. Ooh, okay. So I know velocity is to the right and acceleration is to the right. You guys remember back from kinematic motion, that means that it's speeding up. Okay. All right. Rock and free fall, no air resistance. Rock and free fall. What are you guys gonna draw? Boom, done. That's it. That's the entire thing. Okay. Actually, what if you threw the rock at like a 45-degree angle in the air and it goes into like a parabola path? Every single point on that parabola path, doesn't it have the exact same free body diagram, which is that right there? So would you know the direction of motion of that rock based on that free body diagram? You have no idea. It might be falling straight down, or maybe it's going straight up, or maybe it's going to the side, or maybe it's going at an angle. What you do know is that it's in free fall, right? But you don't actually know its direction of motion, right? You said too? All right. Next one. Let's have a rock and free fall. Let's have air drag. And I will specify one more thing I should have written here, is that let's have it going straight down, right? So go to the edge of a cliff and just drop a rock and it's falling, right? Ooh, with air drag. Ooh, I think this is the first time we're starting to bring in air drag in this class, right? We've normally been ignoring that, right? Let's say this rock has been falling so fast and is through the air that air drag is actually starting to be a significant factor now, right? Did you guys draw a weight acting down, of course, right? And if it's falling straight down, then which direction is the air drag pointing? Like straight up, right? To oppose that motion, which would be like that, right? If it was traveling any other direction, air drag always opposes the motion, kind of like friction, right? Okay. Ooh, guys, is this rock still accelerating? Yes, because there's a net force, right? Is it accelerating at 10 meters per second squared? Not anymore. Maybe it's let's go with 1 kilogram, weighs 10 newtons. I got 10 newtons downforce. Ooh, look at the magnitudes of these arrows, these vectors. Is the drag force about half of the weight, do you guys think? Let's call that about 5 newtons. Guys, what is 10 newtons minus 5 newtons? It's 5 newtons. So you guys see a 5 Newton net force, right? 10 minus 5 is 5, right? 5 newtons acting on 1 kilogram. How much is it accelerating? 5 meters per second squared. Ooh, that's half the original acceleration. So it's still speeding up, just not as much as it was before. Do you guys think this drag force has something to do with how fast it's falling? How fast it's falling, right? So the fact that it's still speeding up, do you think the drag force is still picking up? Up, right? Ooh, we're getting at a new concept here. Let me flip my screen over because I got a new concept I want to show you guys, right? Now, what I'm about to show you guys here about drag force, AP doesn't actually quite go this deep, but I think this is good to know, right? So big picture context, what's going on. Right. So how the dynamics work with air drag, right? Well, without air drag, of course, it always just looks like this, right? This is through a vacuum, right? Free fall. Right, but with air drag, okay, you guys just saw this, picks up to speed, air drag starting to pick up, right? So it's still accelerating. The faster it goes, the more air drag picks up. But that process stops when the air drag matches the weight. Because at that point, now, is this object in equilibrium? Yes, it is. Does that mean it boing, just stops midair? Is that what that means? No, that means it does what? Stays constant velocity. It stops accelerating, right? But constant velocity goes constant velocity all the way down. But it can't pick up any more speed, so the air drag stops picking up. And there's a term for that. Guys, what's that term called? Terminal velocity. You guys ever hear that term? Terminal velocity? That's what I was talking about. Actually, this next slide, I think, is going to probably help give more context. Maybe I should have shown this first. Right? What is the expression for drag force? That would probably be really helpful to know. Right? So here's the full equation for this. The AP, I've never seen AP ask about this, but again, probably good to know anyway. Right? Drag force is proportional to the speed squared, right? So yeah, the faster it goes, the more drag force picks up, but that's the squared relationship. For example, suppose it's falling at some speed, there's some drag force, and it picks up to 3 times the speed. Guys, 3 times the speed is how many times the drag force? 9, because 3 squared, right? I should ask you, 3 squared. You guys would have said 9, right? Now, what else enters into drag force? The cross-sectional area, right? Oh, that's why parachutes are really big, right? Guys, do you want to jump out of a plane with a parachute that's this size right here? Right? Hey, I got my parachute. Hey, we jump. No, because that's a little tiny cross-sectional area. That's not going to do very much good for you. Okay? Also, this Greek letter rho represents the density of the fluid, like density of air, right? If this was falling through water, it would be about 1,000 times the drag force, 1,000 times the density. Right? And also something called coefficient of drag, which is something to do with like the shape of the object. Actually, I have a whole poster for that just to show you guys what I mean. Right, here's drag force. Right, let's focus on the coefficient of drag. Here's different objects falling. Here's a baseball falling. Oh, like 0.47 right there for a baseball. Right, and then different objects, different types. Right. Ooh, parachute. I hope a parachute has a large coefficient of drag. Right? That would probably be helpful too. Right, slow you down in a hurry. Right, you see that? But let's do one more thing with drag force. One more thing with drag force. Right. Let's do. Again, I've never seen AP ask a question about exactly like this, but I could see them asking something like this. I don't think this would be completely out of line for the speed off our case, right? Let's do a velocity versus time, dropping a ball off a cliff, right? So are you guys in your notes saying drop a ball off a cliff, right? Just something like that, right? You guys made a velocity versus time set of axes, velocity versus time. Right? But now we're going to consider air drag. Put that in your notes too. Say with air drag, okay? Because this is going to look different than falling in a vacuum. All right, velocity versus time. We're just going to focus on that one graph, velocity versus time. With air drag, take a quick walk around the room. wonder who's going to get this. Because if you can figure this out before I show you the solution, that's a good sign that you know how to think about physics. All right, let's see who's going to get velocity versus time with air drag. With air drag, you guys figure out what that's going to look like. Got Max has figured it out. Sarah's figured it out. Who else is going to figure out? Eli's figured it out. Looks like Addie's got it. Catherine's got it. All right. Melissa's got it. Okay. A bunch of guys have figured out exactly what that looks like. And what I would think is like when you first drop the object, it's not traveling fast enough for air drag to probably make a huge difference. So I bet during like the first second of falling, it's probably going to be pretty close match with just falling through a vacuum, right? I was going to ask you guys, what does it look like through a vacuum? But you guys would have said a straight line, right? Straight line relationship where the slope represents the acceleration, in this case, like free fall gravity, right? So that's how it starts out, probably pretty close to a vacuum situation. But fall long enough, right? It's eventually going to do something like that. So that if you've got a super tall cliff, it's going to eventually reach terminal velocity where it just can't speed up anymore, right? Like asymptotically approach that velocity. That's terminal velocity, right? You guys got that? All right, let's go back to PowerPoint. All right, so, okay, next one, rock and free fall with air drag, terminal velocity. See, you guys got terminal velocity? It's got weight down and the drag force up, and those two are balancing each other out, right? Now, are they balancing out because of Newton's third law? No, they're balancing out because it reaches a state of equilibrium. But let's go to Newton's third law. Guys, what is Newton's third law to the Earth pulling down on the block again? Does the block pull the entire Earth up? Yeah, that's the opposite force, right? Right. But which force is bigger? The Earth pulling the block down or the block pulling the Earth up? The same. They're equal. Equal. Right. And then how about this drag force? The air pushes up against the block. Does the block also push down against the air? Right. That would be the third law there. Right. A boat moving through the water at constant velocity. Boat constant velocity. Right. Ooh, I gave you guys a direction of motion. Maybe that's good for context. Maybe someone needs drag force possibly, right? Right. Did you guys say this boat has a weight? Boat has a weight, right? What's holding the boat up? Buoyant force, right? Buoyant force, right? Buoyancy, right? That buoyant force. Ooh, I think I briefly mentioned this yesterday. You guys hear something called Archimedes principle, right? The magnitude of that buoyant force is equal to the weight of displaced water, which is proportional to the volume of displaced water, which is less than the volume of the boat, unless it's a submarine, right? Okay, so that's what's keeping it afloat, right? And then maybe the propellers like pushing against the water, driving the boat forward, which is also pushing the water back. Think about it, right? Third law, right? Could that answer that question, or am I missing something? I am missing something because that boat's not constant velocity because there's a net force. I need a what force? Yeah, like a drag force. All right. And the drag force will oppose the direction of motion. Right. Just like friction. There you go. Drag force. Okay. All right, everybody doing good. Doing good. All right, let's go on here. Oh. All right. Can you guys figure out how to draw three forces to put an object in equilibrium? Right. Now, I should tell you guys too, that's not, those two objects are not interacting with each other. I want to show you guys two possible solutions. There's many solutions to this. Can you figure out at least one solution? All right, take another quick trip around the room. Can you figure out at least one solution to this before I show you? So how can you have three forces and put the object in equilibrium? Three forces in equilibrium? Is that possible? How do you do that? Oh, all right, I got a table of winners here. All right, Catherine and Melissa figured it out right away. Let's go and figure this out. All right, three forces in equilibrium. All right, Connor figured it out. All right, Steve figured it out. Phil's gonna figure out how can you put three forces in equilibrium. Three forces in equilibrium. That's the thing. Three forces in equilibrium. All right. I probably got a couple other winners too. Yeah, I'm sure I missed a couple of you guys. Right. But let's flip back here for a moment. Do you guys remember? Boom, that right there. Hey, there's 1, 2, 3 forces in equilibrium right there, right? You know what else that reminds me of? Do you guys remember the donkey problem? Donkey, right? So the donkey's sitting here at rest. I don't know, it's on donkey maker, right? And there's like two guys like trying to pull it, kind of forward to the left, forward to the right, and the donkey probably some friction forces pulling back. That'd be like 3 forces in equilibrium, right? Or like this yesterday. Yesterday we went through analysis with this. We introduced, say, a Cartesian system broken into, say, like components. Everything has to zero out. Right? That'll be equilibrium, right? All right, so you guys remember that. All right. So what else could possibly work here? Got, oh, there's that upside down. Right. Or maybe how about this? What if we're up in a helicopter, looking down, aerial view? You can see 3 guys playing tug of war. You guys see that? 3-way tug of war? Right. Oh, hey, how about something like that? 10 newtons up, 5 and 5 down. That could work too, right? Something like that. Yeah. All right. Parachuter before terminal velocity. Oh, I guess we kind of done this already, right? So you got the weight down, and there's a drag force up. Maybe he's just opened his chute, so there's still a net force. He's still accelerating. Not at the full rate of gravity, though. Right. Parachuter at terminal velocity. Here's what we're looking for. So that's the point of a parachute. Okay, so there's this weight. You got a drag force that's exactly opposed on that. Right. So now he's in equilibrium. Right. And that drag force was proportional to how fast he's going. Also, how big is the parachute cross-sectional area? Something to do with that. Right. Those things. The density of the air matters. Okay. Right. Ooh, here's a good challenge right here. A rocket moving at constant velocity, 10,000 meters per second in deep space. Screaming through space, constant velocity, 10,000 meters per second. Actually, I guess that wouldn't make a sound. It's in space. There. 10,000 meters per second, screaming through space. The forces on that guy. All right, Melissa figured it out. All right, Coast got this figured out. Prana got it. Looks like yeah, Reese has got it. Ooh, all right, Steve's got it. Got here. I think Max got it. Yeah, you guys are figuring this out. You're right. What forces? None. There are no forces on that guy. Yeah, because it's just going, right? Because constant velocity, what's the acceleration? 0. So what's the net force? 0. If it's in deep space, let's see, there's no gravity forces anywhere nearby. It's just going, right? It's just going, isn't it? Hey, you know what this reminds me a lot of is law of inertia. You guys remember this guy? Hey, you guys remember Voyager spacecraft? That's like the same type of story. There's no forces there. It's just going. It's just coasting through space. Right? Just let it go, right? There's no forces there. Right? Guess that. All right, let's flip back over here. Yeah, so you guys are looking at the answer on the screen right there. No forces. Air hockey puck moves across the surface at constant velocity. Okay. So suppose you already set the air hockey puck in motion. Maybe you like hit it a fraction of a second ago. So now it's just coasting across the air hockey table. You guys have played air hockey, right? Air hockey. Okay. This is my go-to example for like a low friction system or a zero friction system. If I ever say air hockey table, so like pretty much get rid of the friction, right? Right. So that air hockey puck is scooting across the table. What does the free body diagram look like on that air hockey puck? Right. Did you guys say air hockey puck has a weight pulling it down? Right. What's holding it up? Those air jets, right? You guys ever feel an air hockey table? Right? All those little jets of air, right? Hold it up. There you go. Right. Kind of like a normal force, sort of, right? Something like that. If you just had that free body diagram with no other context, if you just had the free body diagram, would you know if that air hockey puck was at rest or in motion at constant velocity? No, you wouldn't know. It could be either one. hey, if you're an ant crawling around on that air hockey puck, would you be able to feel the difference between being at rest versus constant velocity? No. Are you in motion right now? Maybe it depends on your definition. Right? You might say you're at rest, or you might say, well, hold on, maybe I'm on a spinning planet, right? But you can't really feel the difference. Right? Yeah, okay, yeah. If it stops, that would be an acceleration. Yeah, feel that, right? You'll splatter against the east end of the wall at 1,000 miles an hour. Earth and the moon. Earth and the moon. Okay, so this would be like two free body diagrams. Maybe we got like a system. Maybe we'll think of this sort of being like a closed system, right? Ignore the other gravity forces in the solar system for a moment, right? It's got the Earth and the moon. Okay. So we're just going to focus on those two, the Earth and the moon. Right. Do a free body diagram for each one of those, like a double free body diagram. Okay. Are those two pulling on each other? Right, some kind of gravity attraction. Okay, so the Earth's pulling on the moon. The moon is pulling back on the Earth. Right? Now, which of those forces did you make the bigger force? I still get you all day. I'm gonna trick you guys. Yeah, it's the same force, right? I'm gonna do F sub G, like gravitational force. You can also represent weight that way, F sub G, like a gravitational force. I'm not gonna do M times G for this because I want to look at like more like universal. There's a more universal form of gravity. Like out here where the moon is, there's definitely a different gravity field than like on the surface of Earth, right? M times G I reserve for like at the surface of a planet, right? So this is like future content, right? This has something to do with the moon being in orbit. We haven't quite got to orbital motion yet, though. Right, and roller coaster. Right, so let's look at this roller coaster at different points. Let's start at top of hill. What if it's like either at rest or like real slow, like click, click, click. It's about to plummet down, but it's just at the top of the hill, right? What's that going to look like? Top of the hill. Roller coaster. Did you guys say there's a weight and a normal force? Right, they're pretty well balanced out. Right? You know what I should have done? What if let's change the situation a little bit? What if the roller coaster is moving pretty fast over the top, like going pretty fast? Now, if it's going pretty fast over the top, do you feel a little bit heavy or a little bit light at the top? You do. You feel a little bit light, right? Does Earth's gravity force on you actually change? No. So your weight's the same. Your weight's the same, right? But maybe your apparent weight changed, right? Kind of like if you stepped in an elevator that's accelerating down. Ooh, it feels kind of like that, right? What do you think would happen to the normal force for the case where you go over pretty fast? Think it decreases? Yeah, I think it would. Okay. In fact, at an extreme, what if you fly over real fast, like zoom, right? Everybody, right in my life, I'm flying off this thing, like fly off the track, right? But that normal force probably shrink to pretty close to zero. Ooh, right? Think about those things, right? Okay, but here it looks like it's either at rest or going click, 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 just real slow. Okay. All right, you guys ready for next slide? All right. Now we're going to send that roller coaster plummeting down to the bottom of the hill. Right. Notice I'm putting it in motion. Right. So it's moving really fast. Right. Now, this one's a little tricky. May not be what you thought it was. I'll give you guys a minute here to see if you guys can figure this out. Right. So it is moving. It's on. Ooh, notice it's on this curved path. It's on this curved path. So that as it moves to the right, it can't actually travel in a straight line. It's going to be forced to go up at the same time. We're starting to get into this idea of like something with like changing direction. There's some kind of force associated with changing direction. Right. Would you feel really light or really heavy at that point? Heavy, right? As long as you're in motion. In fact, I bet the faster you're going, the heavier you would feel. You're on that curved path, right? So did you guys draw the same way as, I mean, the gravity pull doesn't change, same way. Right? What did you guys draw for the normal force? Really small or really big? How about really big? Yeah, really huge normal force, right? There's like some scale at the bottom. That scale would read like more than the weight of the track, right? Of the coaster, right? Is there a net force on that coaster right there? There is a net force. It's upward, right? That force is going to be called the centripetal force. And that centripetal force has an equation that goes with it that's related to how fast it's moving, that v, speed, and also the radius of curvature, and also the mass of the car. Right? All those things are related to centripetal force, the net force. Okay. That'll be a future content. Right? What about at the top of the track? Right? So it's going around this loop, around the top of the loop, right? So it's still in motion. It better be in motion, right? Because if it wasn't in motion, it would just fall off the track, right? So definitely in motion, but it can definitely get around. What's going on with the forces right at the top there? Did you guys say, does it have a weight pulling straight down? It's got a weight pulling straight down, right? Right. Which way does the normal force from the track point? Also down? Ooh. Is there a net force on that cart? There definitely is. And like in a hurry, it's straight down. That's it. That's the answer to that one. Okay. Last thing today. Oh, we got an extra minute here. So earlier classes were asking about something to do with like G force. You guys ever hear the term like G force? Like how many G's? Okay. Which actually isn't a force. It's more of an acceleration concept. This guy's sitting in a centrifuge. I think he's doing like fighter pilot training. You guys know centrifuge, right? Spin him in a circle. You guys see his G counter up in the top left? See his G counter? All right, let's see what happens. Exactly. Multiples of the gravity field. We're all sitting in 1G right now. Got it in. Ooh, 9 Gs. He's in 9 Gs. Yeah, but he all right. He all right. Yeah. Good morning. You're in a centrifuge. You almost died. All right, let's wrap on today.